and excretion. Okay, so this is a system you have to maintain homeostasis with ion concentrations. Okay, if sodium concentration too high, it's bad, too low, it's bad. Okay, and also pH. pH has to stay in a narrow range. And the evolution of osmotic regulatory systems originally was for maintaining homeostasis with ion concentrations and pH. Then later, in other clades of animals, the same types of organs have evolved into excretory organs that also now include taking care of metabolic waste. Since animals do not have cell walls, osmotic pressure is very important, because if solute concentration inside a cell is higher than solute concentration in the medium surrounding, then water will enter into the cell by osmosis, okay, down concentration gradients. And therefore, the cells, since they have no cell walls, they will stretch and burst, killing the cell. But on the other hand, the solute concentration in the surrounding medium has a higher solute concentration than inside of the cell. The cell will lose water. Water will go down the concentration gradient out of the cell, and the cell will shrivel and usually get contents too concentrated to maintain life, and they'll die. So either direction is bad.
Isn't that like hyper or hypotonic?
Is that like what?
Hypertonic or hypotonic?
Yep, it's related to hypertonic, hypoosmotic, and I'll come up to those terms here in a moment. So osmosis, and so the water is being moved by osmosis, okay? When we get into the interstitial fluids, that's the only way water moves in and out of cells, okay? The only pump we have for bulk flow of fluids is the heart in the circulatory system, but when we're at the level of cells, the movement of water is by osmosis, okay? Across semi-permeable membranes. Okay, so we have these terms, this is what you were referring to. If the surrounding medium and the internal medium of a cell have the same solute concentration, that's called isosmotic, okay? And in such a system, there's no net change of water moving into or out. However, if one of the media happens to be hyposmotic, the other one has to be hyperosmotic. And the flow of water would be from a hypoosmotic into hyperosmotic. Okay, because this is high solute concentration, but where the solute concentration is low, the water concentration is high. Where the solute concentration is high, the water concentration is low. And therefore, this osmosis is indeed the diffusion of water from an area of high water concentration to low water concentration. But that water concentration is hard to measure. We can very easily measure the solute concentration. Okay? So this is what's happening with osmosis. And in your kidneys, when we get toward the end of this is exactly how water is being manipulated. Is first of all, we have pumps that move solutes to create a concentration gradient, and water follows osmotically. Yes?
Did you say that it flows from hypoosmotic to hyperosmotic?
Yes. Yes. Hypo to hyper. All right, so life evolved in the oceans, and a lot of our solute concentrations in many animals is composition of salts is very, very similar to ocean water. However, with terrestrial animals and freshwater animals, they have changed a little bit. Most of the marine animals are osmoconformers. That means the solute concentrations inside their cells, their interstitial fluids, is pretty much the same as outside, okay, in ocean water. Therefore, they don't have to adjust their internal osmolarity. Okay, now I'm putting up a little bit of a different term here. This here, extracellular fluid, is the same as interstitial fluid. Okay, this is just another term. You'll come across it. But they mean the same thing. It's still the fluid that's bathing the cells. Okay, extracellular fluid. So for most of these marine animals, who have an ancestry of being in marine water, they're isosmotic to the ocean. All right, so they don't have a problem with water moving in or water moving out. However, that doesn't mean that they're identical necessarily, their solute concentration is necessarily identical to what's in the ocean water. It really depends. If they are ionoconformers, then the concentration of sodium, both inside their bodies and outside of the bodies, is isosmotic. Chlorine, isosmotic. Phosphorus, isosmotic, etc. So all ionoconformers are by default osmoconformers. Osmoconformer means that they're osmotic, their body fluids are isosmotic to the seawater, okay? But it doesn't necessarily mean that the ionic composition will be the same. These ionoregulators, they are osmotic to the surrounding water, but they may maintain a higher sodium concentration and a lower chlorine concentration. But when we're looking at the osmolarity, it's the total amount of solutes. So the solute concentration collectively is the same, but not necessarily the ion concentration. Sodium might be higher, magnesium might be lower, but they balance out isosmotic, but not necessarily identical inside and out.
Would the ion concentrations be lower to like, because there would also be like proteins and stuff in like organisms?
Yeah, and that happens, yeah. So those, and there's quite a few of those because of the protein concentrations that actually they have to be ion regulators. So they have to regulate maintaining sometimes a lower sodium concentration in the water, okay? But there are others, like, for example, cnidarians. Most of them are just pure water, and they're ionoconformers, okay? Because they don't have a whole lot of free proteins that would be created. The proteins are in cells a lot of times, and furthermore, there's so much mass there that is extracellular matrix that they can get by. But a lot of them happen to be ion regulators. Okay. Okay, now, this means these don't have ion conformers. They don't have to expend any of their energy because the salts, magnesium, phosphorus, same inside as outside. But those that are ion regulators, however, they have to maintain that because ions will keep leaking in or leaking out of their body, okay, because there's still leakiness. And therefore they have to use ATP-driven pumps to continuously keep constant ion concentration. Okay, they have to be pumped against gradients in order to maintain their ion composition. And we'll look at some of these as we go on. All right? Okay, so emphasizing here that those, so you have to keep these separate, osmoconformers from ion regulators, ionoconformers. Okay, here with the ionoconformers, or regulators, extracellular interstitial fluids still has the same total ion concentration, but not necessarily the same concentration for each and every different ion. Because osmosis doesn't matter what the ions are. It's only the quantity of solutes. Okay, then on the other hand, we have osmoregulators. Here, they're interstitial fluids. Extracellular fluids are not isosmotic to the surroundings. All terrestrial animals are ion regulators, okay? All animals that live in fresh water, not in the ocean, have to be ion or osmoregulators. Yes?
Are ionoregulators a part of osmoconformers?
Yes, it's under that. Osmoconformer is broader, okay? That's a concept that means that they're solute concentrations inside the body is in equilibrium with outside the body. Totals, okay?
For
But with an
osmoregulator.
ionoregulator, although they're osmotic, they don't have the same percent sodium, same percent phosphorus, same percent chlorine as in the seawater,
Okay.
okay? Just to give an example, say that, in the water, sodium is millimolar, and let's say chlorine is also 0.1 millimolar. Say magnesium is 0.3 millimolar. Okay, so all those add up to 0.5, right? Okay, so with an ionoregulator, it might have 0.05, 0.05, and 0.4. Okay, it still adds up, total ion concentration, isosmotic.
So
But
like
not the concentrations here, they're different.
that could be like the ocean, and that's the ion
This would
regulator.
have to be an ion regulator,
Okay.
because we would have sodium leaking in, that leaking in, and this leaking out, because they're trying to reach equilibrium. And to maintain this is that we have to have pumps that will continually keep the balance. Requires energy.
What's an example of an ion regulator?
Well,
Like, is
I'm
it-
not real sure
is
which
it
ones
something
are
in our
ion
bodies
regulators,
or
but they're
some-
all marine. They're all marine,
So it's something in like a marine organism's body? Okay.
but not all. Okay,
Yeah.
not all of them. All right, so sharks. I'm going to get to sharks here in a moment. You have a question?
So, yeah, so is it possible for an osmoregulator to be an ionoregulator?
Osmoregulator, they have to be. Yes. So an osmoregulators are ionoregulators. It's impossible for an osmoregulator to be an ionoconformer. That's a category that doesn't exist.
An osmoconformer can be both ionoregulators and ionoregulators?
Yeah, yeah. So with osmoconformers, they can be either one, okay? This here would be an osmoconformer, because the total solute concentration is the same. There's no net flow of water. But it's an ionoregulator because it maintains different ion composition compared to the ocean water around it. Now, if I made this 0.1, 0.1, 0.3, then that would be an ionoconformer. Does that make sense?
Yeah, okay.
Yeah, but it's impossible for these, if it's a regulator, it regulates the ions, okay, by default. Okay, so they have to continually adjust the osmolarity. And this requires a transport epithelium. Okay, epithelia are very important, and we'll look at this. Furthermore, these are regulating the concentrations, that's what I said here, because we get leakage, it might not be real fast, but it's still something that continually has to be corrected, all right? Because this is now the condition in these animals. And therefore, and furthermore, these also usually are adjusting pH as well. Now, by adjusting the ion concentrations, they are adjusting the water concentration, because the water will follow ion gradients, okay? So water, there's no pumps at the cellular level to move water. No pumps at that level. Okay, so The only way in which water can be moved from one compartment to another is to pump solutes out of one compartment, so the solute concentration is higher on one side of the epithelium, and water will follow by osmosis. And of course, that requires energy. Okay, now getting back, you wanted an example. I can't, right off the top of my head, I don't know which of these marine animals are ion regulators or not. Most of the marine organisms that evolved in the ocean have an ancestry in the ocean and never have any ancestry of living in fresh water. Most of them are osmoconformers, but some of them are ion regulators, some of them are not. Okay, so, but there are still some marine animals that have an ancestry of having lived in fresh water and then returning to the ocean, that they end up being osmoregulators. All fresh water, because what is the solute concentration in fresh water? Very, 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 very low, okay? And there's no way you can have a living organism with that low of solute concentration, and therefore they have to regulate it, because they're constantly losing, especially fish, because they have all this fresh water going through their gills. Wonderful place through the lamellae to lose salt, okay, solutes, yes.
So osmoconformers can be ionoregulators, or ion regulators and ionoconformers, but osmoregulators can only be ionoregulators.
That's right.
Okay.
There's no such thing as a ionoconformer that is also osmoregulator.
Okay.
That's a category that just doesn't exist. And of course, all terrestrial animals. Because why terrestrial animals like this is because we're not living in water. We don't have to worry about water coming in. It's losing water across our skin, through our lungs, and everything like this. Furthermore, in order to, in your diet, you're taking in sodium, chloride, other things, other salts that you have to avoid. We have to get rid of urea, and there's no way to get rid of urea without losing water. And therefore, in the terrestrial sphere, water loss is a big deal, okay? And so this leads to osmoregulation. Okay, there's a statement. All osmoregulators are also ion regulators. But the other category doesn't exist. Osmoregulator and ionoconformer, those are contradictory. They don't exist. Okay, give you an example. We believe that all gnathostomes, the ancestors of gnatostomia, probably evolved in fresh water. Okay, they probably evolved in fresh water. Now, marine vertebrates, however, the original ones, ancient ones, evolved in marine habitat. Hagfish are isosmotic. Hagfish are also, I believe, ionoconformers as well, okay? But not gnathostomes, okay? Gnathostome. So here, originally isosmotic. We believe that the ancestor of the gnathostomes moved into fresh water, okay? So what's going to be the problem with them? They originally were isosmotic. They move into fresh water. What's going to be their relationship with the water around them? Okay, so in other words, which direction will water tend to move?
Into their bodies.
Into their body. Okay, so they have a problem with water moving in. Because now they're hyperosmotic to the water, and therefore they move it in. Some of this water is moving through the skin, but most of it is entering through the gills, because there we have just a thin epithelium in the mamella, where water where we have blood and water real close together, and we get salts leaking out and water moving in. So over evolutionary time, the adaptations that had to happen here is this. these are the long-term adaptations, is that they had to have excretory organs or osmoregulatory organs that would produce a large amounts of dilute urine. Okay, what do I mean by dilute urine? It doesn't have a lot of salts in it. Okay, because they're also losing salts across their gills, because low solute concentration in the water, they're losing it. So we need to have lots, and they have a lot of water moving in. And so therefore they've got to get rid of large volumes of water to maintain homeostasis, but try not to lose all their salts, okay? Furthermore, their gills have sodium chlorine pumps in the epithelium, in the lamella, that use active transport to take up sodium and chlorine, okay? So it's actively pumped out of the water into the blood. And further, another long-term adaptation has been to lower the gradient between concentration solutes in the body and in the water. Now, they can't lower that gradient all the way down to where they're isosmotic. That's impossible. But nonetheless, the solute concentrations in freshwater fish is less than in marine water, okay? So decreasing the gradient a little bit still saves a lot of energy. Now, some of these fish have, so these are the ancestors of Chondrichthyes stomati, okay, and Osteichthyes. We also believe that that's true of sharks and cartilage fish, that they have evolved in freshwater. And then they've returned to the marine habitat. Okay, now what's happening now? They've undergone this millions of years of reduction of solute concentrations, and they now return to the marine environment. They're now hyposmotic compared to the marine osmotic. So what's going to be the problem here?
Water will escape them.
They have a tendency to lose water, okay? They have a tendency to lose water, and so the adaptations here, and this has been a mystery. This is why it's basically based on physiology of marine fish and sharks, that we believe that the ancestors of naphthostones evolved in fresh water, because this doesn't make sense, because other long-term marine animals are all isosmotic, okay? No problem. So the adaptations that these have had to make is that they drink like a fish, okay? They have to drink large amounts of water to replace this water that's being lost. But as they're doing that, they're also taking in a lot of salt, okay? They're also taking in a lot of salt. Therefore, they now have gills that have these pumps, sodium, potassium pumps, and so forth. They're reversed in the lamellae, still using active transport to pump them out, okay? Because they're getting a lot of salt, okay, here, and they have to pump it out, because they have to maintain a solute concentration that's lower than in the marine habitat. And furthermore, their kidneys, which are now excretory as well as osmoregulatory, they have to produce a small amount of concentrated urine. Why concentrated?
So keep them.
Because they're taking in all this salt. Now, usually what's happening here in the gills is it's mostly the gills are mostly regulating pumping out sodium, chlorine, and I think probably potassium as well. The kidneys, however, are taking care of things like magnesium, phosphates, and other types of salts that are in the marine water. So this has to be concentrated. Why concentrated? They're losing water. You don't want to lose more water with the urine, okay? And so they've adapted in that direction, okay? Okay, so this is regulating the salt and water balance. Now, let's talk about sharks. Sharks are isosmotic, but yet their solute concentrations when it comes to mineral salts is lower than the marine water. What trick do they use to be isosmotic is that they produce and they have evolved a system that they can tolerate high levels of urea. And therefore, they store a lot of urea in their body fluids, and that makes them isosmotic, the urea content. Okay, but it requires also a certain type of protein, I forgot what it is, that prevents a lot of the proteins from denaturing in the presence of high concentrations of urea. Yes?
Isn't it also because you have oil in the liver that is like?
That's mostly for
isosmotic?
buoyancy. Yeah, that's mostly for buoyancy. Because they don't have swim bladders to adjust their buoyancy. That, the oil is mostly for that. But as far as being isosmotic, it's primarily the urea. Yeah. Okay? Now, in turn, don't have a lot of time here left, but there was osmoregulation, regulating the ion composition of the body and the water content. But we also have metabolism of protein, nucleic acids, producing ammonia. Okay, these are from amine groups, and it's highly, highly toxic. However, it's also very, very soluble in water. Therefore, those animals that are small, they don't have to have any sort of excretory system. So when we're talking about getting rid of this metabolic waste, that's excretion. They don't have to have any special type of epithelium to get rid of it because it can just diffuse out. If they're small enough, okay, simple diffusion will take care of it. But as we get bigger, then we have a lot of cells that are producing ammonia that they're not close enough to the water on the outside. Simple diffusion doesn't work. And therefore, they have a problem. And therefore, we have to evolve a special type of organ for excretion as well. Okay? Now, these excretory organs generally are osmoregulatory organs. They evolved first as osmoregulatory, and now they're taken on a secondary function of excretion, getting rid of metabolic waste. So, I have already emphasized this before, excretion and elimination are not the same. This word excretion is used only for getting rid of metabolic waste that are already inside of the body. Elimination is getting rid of undigested material that's in your digestive tract. It was never in your blood system before, okay? Okay. Now with terrestrial animals, this getting rid of ammonia is really problematic because you can't get rid of it without losing a bunch of water, okay? And if you're excreting just only ammonia, the amount of water needed to keep that from being too toxic is very massive. You would lose a lot of water. And that's already a problem with terrestrial animals. So what happens is that either the urea is combined, or excuse me, the ammonia is combined with carbon dioxide to form urea. Urea is a lot less toxic. Now still, to excrete it requires water. Okay, you still have to lose water, but you wouldn't be losing as much water as with just only ammonia. Many reptiles, including birds, have something else. They converted the ammonia into uric acid, which has it's far less toxic, and it's very low solubility in water. They excrete it as a solid. It's a white substance. So when that birdie flies over you and that white thing jumps on your shoulder, okay, that is uric acid, okay? It contains a lot of uric acid, solid. And therefore, they don't lose as much water. Okay, so this is the rundown. This is where I'll stop for today. In actuality, all these animals have all three forms of this nitrogen. We still, in our urine, have some uric acid, but not much. It's mostly urea. And we also have some ammonia, okay, but it's a low concentration. Whereas in the fish, they don't have to worry about it, because the ammonia will go just right out their gill lamellae, okay, because the ammonia is very soluble in water. Birds, mostly uric acid. Okay, so this is where I'll stop for today.